the topic, subsonic flight. Yeah. So under our title, the decay model, this one you can see, it's the phenomenon is different. It's not a radioactivity, different, but it follows the same law. Remember the decay law. Decay law, so we generalize it. Yeah. So if the function has the same property, so then we can apply the same law. Yeah. All right. First, let me give you the question. Yeah. Our problem number 2, subsonic flight. The question. All right. Efficiency of the engines and of the subsonic airplane depends on the air pressure and is usually maximum at 36,000 feet. Yeah. So here, actually this sentence is not quite clear. Yeah. So efficiency of the engine depends on the air pressure. Yeah. So here we just take this fact. Yeah. Is usually maximum. So this means this airplane, the maximum height it can fly is this much. Yeah. The maximum height. Yeah. This plane. Yeah. Then air pressure at the maximum should be the smallest, right? Because the higher, then the air pressure lower, right? Yeah. Air pressure lower. Yeah. Air pressure lower, then the efficiency also lower, right? Yeah. Because it depends on the air pressure. So we connect. So there is a, direct connection between the efficiency of the engine and the air pressure. Yeah. All right. But in this question, we focus on the air pressure, not the efficiency of the engine. Yeah. Yeah. Closely related, but we study the air pressure. So the air pressure, we treat it as a function. We need to find air pressure function. Let me give you more information. At 18,000 feet, it is half its value, y0. Y0 is at a sea level. Yeah. All right. At a sea level, air pressure is y0. Air pressure at a sea level is given, although we do not have the specific number, we just use the symbol y0. Yeah. We treat it as a known value. Yeah. But at this height, 18,000 feet, the pressure, air pressure at this height, half the value, half the y0 value, half this, one half of the y0, also given. Yeah. So with this known information, now the question. Find the air pressure function y of x at this height. What height? The maximum height. Maximum height. That's unknown. Yeah. The air pressure at the 36,000, that the maximum height, that air pressure is unknown, so we need to find that value. That's the question. Okay? Yeah. All right. Oh, yeah. So okay. Yeah, here I have some annoying symbol, but you do not see it. Good. First, let's do some analysis, the physical law. Yeah. To do the modeling, we need to apply appropriate physical law here. Yeah. So what's that? Decay law, similar to decay law. Okay? All right. The rate of change y prime of x is proportional to the pressure. Pressure y. Y is the pressure function. So y prime of x is proportional to y. That's the decay law, right? Yeah. Yeah. Same law. Same law. Yeah. All right. But the variable is slightly different. In our decay law, our variable is time t. Here, the variable is height. X is the height number. Height. Yeah. So y prime of height variable. Yeah. All right. Yeah. Analysis. Now, we need to set up an equation. Based on this physical law, let's write a ODE for this one. Yeah. Here, apply our problem-solving strategy. Another simple strategy, but this time, our strategy becomes use our experience. Yeah. Our 8.1 is our experience. Yeah. So this time we have 8.1. Yeah. So we can borrow the experience from 8.1 immediately. Yeah. All right. So this is the equation. Yeah. C constant. Yeah. There is a C constant. Yeah. Could be positive, could be negative. If it's a negative, then decay. Positive, increasing. Yeah. All right. Yeah. Yeah. But in our original decay model, we need to modify it slightly. Yeah. But it's not a fundamental modification. Yeah. We just change the variable from t to x. Yeah. Time t. Time t. In our generalization, we can change to any variable. Yeah. Not necessarily time variable all the time. Yeah. So that's the small modification. Yeah. Then let us solve this modified equation. Yeah. Old solution, yeah. We know the solution, right? So last time, we know the solution. Yeah. Last time, the general solution is this form. A constant. There is a constant. Then also another constant, C constant, at the exponent. Yeah. Two constant. So we need to determine these two constant here. Yeah. Two constant. All right. Yeah. But that's the t variable. Yeah. So we need to switch to our newer version with x variable. Yeah. All right. Yeah. So our new solution, it should have this form, y of x. Based on our old experience, we can write the solution form in this way. Yeah. Yeah. Okay. Yeah. So we developed our general solution for the decay model, right? We just use it. Okay. We do not have to develop every time we repeat the development details. Yeah. We just apply the result directly. All right. Then let's determine A and C, and finally we want to find the answer. Okay. All right. Yeah. First, at the sea level means x0, right? So you plug in x equal to 0 at the sea level. Initial value is y0, and it is also a. So that means a equals y0. Okay? So the first constant is determined. Yeah. First constant determined. But C constant still unknown. At this point, C constant unknown. Yeah. So let's leave there, C constant. All right. Next, this time we need to target the air pressure at which height? 36,000, the maximum height. Okay? Yeah, maximum height. Yeah, all right. All right. Our current form of the solution. The given condition so far, yeah, at 18,000, air pressure is 1/2 of the sea level pressure, right? Sea level air pressure, half of the sea level pressure, 1/2 times Y0 at 18,000 height number. Yeah. Find our goal. We need to find Y of 36,000 equals what multiple of Y0, right? Yeah. Yeah. So our goal, we need to find certain multiple. This number equals certain multiple of Y0. Yeah. That's our goal. Solution. Yeah. Constant C is unknown, right? Yeah. Some of you may not feel comfortable. C is unknown. How do we do the calculation? Yeah. Don't worry. We have some way to get around it. Get around C, constant. We do not have to find constant C. We can cancel it out. Cancel it out. All right. Yeah. So let's do the manipulation. Yeah. First equation. Yeah. First equation, we plug in, because we have the general solution form. Let us plug in y equals 1800. Not 100, 1,000. Y of 18,000. Plug in the general form solution. Yeah. So we have this first equation containing that unknown constant C. Yeah, leave there. Leave there. Okay? Yeah. Then we have our second equation. Yeah. All right. Yeah. Here I do some simplification because this equals 1/2 of Y0, right? So after, yeah. All right. Yeah, so here actually I write in this way. But this information, this information is useful. Yeah, so we leave there. We will use it later. Okay? So here we just rewrite. Yeah. Because C unknown. Yeah. So let's write the expression containing unknown constant C at the left-hand side. So right-hand side, we write this expression. Okay, all right. Then, for maximum height, plug in maximum height. Then we have this expression. Okay? And let us write a similar equation in this structure, but for the second equation. Okay? That is e to the 36,000 C equals Y of 36,000 over Y0. Okay, similar structure, both sides. These two equations, together. I intentionally write them together because my current goal, I want to find a way to cancel out unknown constant C. Yeah. Unknown constant C. Annoying. Yeah. Not convenient. Yeah. But we want to find a way to remove it. Yeah. Can you see any little trick we can apply to, gracefully get around constant C? Observation. Yeah. Compare these two equations. What property can you see between these two equations? Look at this part. Look at the left-hand side. These two expressions what is the relationship between them? Yes. 36,000 is twice of 18,000, right? Yeah. Twice. But twice relationship appears at the exponent number. All right? Yeah. Then can we say the bottom expression is square of the top expression square? Twice at the exponent. So that's the square thing. Yeah. So this property, we can use this property to take away C constant. Yeah. All right. But this time, this condition is useful. Okay. This condition, this ratio equals 1/2 based on this known condition, given condition. Yeah. This ratio is 1/2. Yeah. Very simple, right? Yeah. But the left-hand side, this expression is square of that expression. Can we say the fraction, the bottom fraction, is also square of the upper fraction? Yeah. The lower fraction is also square of upper fraction. Yeah. Yeah, because left-hand side, the square relationship. Right-hand side, it should also has that square relationship, right? Think about that. Okay? Although there are different ways to explain the relationship. Yeah. All right, square relationship here. The fraction, square. So based on that, we can, yeah, because the left-hand side has this relationship, right? Left-hand side. Right-hand side, also the square relationship. Okay? Right-hand side, the fraction should be the square of the upper fraction. The upper fraction is 1/2. Square of 1/2, that's 1/4. 1/4. Yeah. Yeah. Try to follow the logic reasoning. Yeah. 1/4. That conclusion. Our last step. The air pressure at 36,000 feet, yeah, equals 1/4 of the sea level air pressure. Sea level air pressure. That's the conclusion. Okay? That's the conclusion. Yeah. Yeah. Same law, decay law. Yeah. Although it's a different, completely different problem. Yeah. But the phenomenon follows the same law. Yeah. Yeah. Rate. So what kind of law? The rate of change is proportional to the original function. Yeah. That law, same law. Yeah. All right. So at this point, I want to talk about this week. Yeah. The work. Yeah. Yeah. Assignment, the work. This week we have 2 classes. We finished 2 classes after this week. Yeah. But I do not plan to give you assignment this weekend. Yeah. But I plan to give you a few exercise questions, self-study exercise questions. So in Canvas, I will post 2 or 3 questions like this, word problems, this kind, to let you to practice. You do not need to turn in. And I will post the solutions next week for self-study. But But next week, I will post our first quiz. First quiz next week. Second week, after second week. Quiz, online quiz. Yeah. All right. For the first homework assignment, I want to, build up a little bit. At least we need to finish Module 1. After we finish Module 1, we have our first homework assignment. That's my current plan. Yeah. All right. Next, any question for this one? Yeah. Let's move to the next question, 8.3, radiocarbon dating technique. This is a famous, very important technique. Yeah. Radiocarbon dating. Yeah. Find the date. Find some very old object. Yeah. Try to determine the age. Age. Yeah. All right. The question here. Let me give you the background of radiocarbon dating technique. Yeah. All right. Determine the age of an object containing organic material. Yeah. How to do the dating? So there is some, very smart idea here. Yeah. By using the properties of radiocarbon, some special isotope, carbon element, substance. Yeah. But there is a radioactive isotope of the carbon. Yeah. So use that. So that's the carbon-14. Carbon-14 is radioactive. Yeah. There are 3 different isotopes for carbon. Okay? 3 different carbon isotopes. And this one is the only one that is radioactive. All right. Yeah. The question, how was this method developed? Yeah. So the history of this method. Willard Libby, this professor, physical chemist, University of Chicago, developed this method 1949, that early. Yeah. And he was awarded Nobel Prize in Chemistry in 1960 with the contribution of this method. So you know how important it is. Very important. Okay? But you will see the method is very simple. Based on the decay model. That's simple. But so important. The impact is huge. Yeah. Impact is huge. The method is so simple, but extremely important. Yeah. So Nobel Prize. Yeah. All right. So here, this picture explains the basic idea of this technique. Yeah, here, let me explain a little bit in this picture. All right. Now, apply this technique. So we want to determine object. So what kind of object? So the object has period of living organism, living, yeah. So tree, horse, human, yeah, living organism, yeah. So start with the living stage, okay, living stage. There, because when those organisms in the living state, there is a environment around those organisms, sun, you know, recycling, you know, right? Yeah. So under that living environment, the carbon-14 level, yeah, because this technique, we need to study the carbon-14 percentage in those objects, percentage. Yeah. But when those organisms in the living state, the carbon-14 ratio is stable. Okay? Yeah? Because there is a natural cycling, right? Yeah? So, you know. So then the level of carbon-14 is stable. Okay? Yeah. All right. And the stable and also at the highest level of those organisms. Highest level. Stable means no decay. Okay? No decay because recycling, right? Yeah. You know. Yeah. If some decay, then you have new, right? So you get it from sun. Yeah. So the new part coming from sun, from other reactions. Yeah. So in the living stage, the ratio is stable. But then after they are dead, then no recycling, right? Yeah. No recycling. Dead. Then decay appears. Carbon-14, the ratio, the level of carbon-14 follows the decay law. Decay law, yeah. Going down. The ratio of carbon-14 going down. Yeah. So then this technique, we just measure the ratio of the carbon-14. So if we can accurately measure the percentage of carbon-14, then apply our decay model equation, we can estimate how long that organism was dead. Yeah. Yeah, yeah. Half-life, right? Remember, you know, those things. That's the idea. Okay? Yeah. All right. Next, let me use an example to explain this method. Yeah. All right. All right. Measuring the proportion of carbon-14. Proportion to what? Yeah. I need to explain a little bit. In a sample from a dead organism provides information that can be used to calculate when the organism died. Okay? Yeah. When? At that point, so die. That's the starting point. Yeah. The time it was dead, that point is the 0 point. 0. Starting from there, how long it takes. Yeah. Measuring the proportion. Yeah. All right. Now look at our problem number 3, radiocarbon dating problem. Yeah, it's a real one. Okay? Yeah. So this question, yeah, the real problem. Real world. Yeah. All right. Oats, mommy. Yeah, that one. Question. September 1991, famous Iceman. The real one. Okay. Yeah. From Neolithic period, Stone Age, Austrian-Italian border. It was estimated that the ratio What the ratio? Ratio of carbon-14 to carbon-12. Yeah, I will explain the relationship. Yeah. Carbon-12 in this mummy is 52.5% of that of the living organism. That of what that? That is the ratio of carbon-14 to carbon-12 of a living organism. Two ratios. Yeah. Two ratios. Yeah. Different time points. Yeah. Yeah. 52.1. Yeah. And the question, when did oats approximately live and die? Yeah, that period. Yeah. We need to estimate, but sorry, sorry, but one important number should be given. Do you know which one? Yeah, in order to calculate, do the estimate. Yeah. We need to know some important number about carbon-14, radioactive substance, half-life. Half-life of carbon-14 should be given. Yeah. That's easy. Half-life of carbon-14 is known. Yeah. So we need to get that information. Yeah. Half-life of carbon-14 is 5,715 years. That long. Okay? Now, we have enough information, we can estimate the age of this Iceman mummy. This one. Okay? Yeah. Interesting, right? Yeah. Interesting. With the radiocarbon dating technique. Yeah. So we can get a pretty good estimate. Now, let's do it. All right. Modeling. Capital H, half-life. Now, the amount of substance. Yeah. Because our goal, we want to calculate, estimate the amount of substance of carbon-14 as a function. As a function. Yeah. That function keeps changing. Yeah. Decay. Yeah. So that's our target function. Yeah. All right. Y of t. Y function. Time variable, t. All right. And initial value, y0. Initial value, that amount, specific amount, not important. So we use y0. Yeah. Yeah. All right. And here, in order to do the estimate, we take approximation way. Approximation. Yeah. Because it's very hard to do very accurate estimate. So we try to make our estimate as close as possible, but sometimes we may need to ignore some little things. Yeah. Otherwise, it's too complicated. Okay? Sometimes in order to make our equation as simple as possible, we need to ignore some little quantities. Little quantities. Yeah. Let me explain. What do we need to ignore? Yeah. There are 3 isotopes for carbon. Total 3 isotopes. The first one, common carbon. So the dominant percentage of carbon is carbon-12. Yeah. Common, not radioactive, keeps the same all the time. Carbon-12. Yeah. same carbon-12 all the time. No change. Okay? No change in the organisms. Rare carbon-13. Carbon-13, another isotope, but a very rare. Okay? Amount, tiny amount, rare. So here we ignore it. So small, so little, because when we do estimate, we ignore that little thing. Okay? Yeah, all right. Then, now, we want to measure carbon-14 over carbon-12. Yeah. So here, although carbon-14, the ratio of carbon-14 over total carbon, right? So this is carbon-14 over total carbon, but in the denominator, C13, rare, very small. So we throw away. Okay? Carbon-14, compare it with common carbon-12, also very small. Okay? Yeah. So the denominator we just used amount of C12 to approximate. Yeah, approximate. So we just use this ratio to represent the percentage of carbon-14. Approximate. Yeah.
Why did we get rid of C14 in the denominator?
C14, yeah, because C denominator, think about C12 dominant. Think about C12, let's think about 90-something percent. Okay, 99, 98%. Yeah. C14, very small amount, but still much larger than C13. Yeah, C13, rare. So even much, much smaller than C14. But C14, not as small as C13, but comparing with C12, very small. Okay? Yeah. So based on that, yeah. So we only need to, for the simplification, we just study this ratio. Okay? We compare this ratio. This ratio at 2 time points. Yeah. The dead time, yeah. So, yeah. Yeah. So after the organism was dead immediately, that time, okay, 0. T equals 0, that time we measure. That one we, that one is the living, right? Yeah, living ratio, right? Yeah, so there are 2 ratios. The 2 ratios, okay? Yeah. And based on the question, the relationship between those 2 ratios is given, right? 52.5%, right? So the ratio of carbon-14 to carbon-12, this mummy is 52.5% of that, another ratio, right? Ratio of the living organism. Yeah? So these 2, one is 52% of the living one. Okay? How about that? Living one. Yeah. But the C12 is stable. No. We can assume the C12 part is constant. During the whole period, C12 is constant. Okay? Yeah. Then they have the same denominator, right? Constant. Same denominator. How about we just focus on the numerator? Numerator changes, denominator does not change. Okay, so we do not need to worry about the denominator. All right. Now, the modeling ODE. All right. Y prime equals KY. Yeah. This is a radioactive decay model, right? Yeah, also radioactive. So we applied our same law, decay law. Yeah. Yeah. So that equation, all right. K less than 0. Decay. Yeah. All right. Solution. We know the solution form. Right? By our experience, the solution should take this form. Yeah. For certain K, K is the decay constant. Yeah. Although negative, yeah, but if we allow K could be negative number, yeah, so it's a decay constant. Yeah, decay constant. All right. Then we plug in the half-life, capital H. Y of H equals Y0 times e to the little k h. Half-life. Okay, yeah. For the half-life, yeah, half-life, this is the meaning of half-life. Half amount, right? At a capital H, the amount of radioactive carbon-14 is half of the initial amount. Half of the initial amount. Okay? Yeah, that's the definition of half-life. Then let us simplify this equation. 1/2 equals e to the kh. 1/2 equals e to the kh. H is known, k is unknown. Can we find the k? H, capital H is known, but the k constant unknown. But we can find it, right? By solving this equation, we can find the value of the decay constant k. Right? Yeah. All right. Yeah. So the last slide, we need to solve. We need to find the answer. All right. Half-life given. Yeah. The meaning of half-life, we derived the half-life equation. Yeah. Our goal, we want to estimate T1. Yeah. Because this time, the current time, the measure 1991, that time, right? The die time and the 1991. So that period, we want that period, we use T1 represent. Y of T1 equals 0.525 Y0. Also, it follows this expression. Yeah? All right. The question, how to find T1? How to find T1? Yeah? Yeah. Pretty easy, right? Yeah, pretty easy. Yeah. Most people, here, I want to explain what's the best way to find a T1. Although there are different ways to find T1. Yeah. Most people, they find T1 in this way. From the first equation, they can find a K, right? Yeah, K could be solved from the first equation. Then plugging into the second equation, because only unknown is T1, so T1 can be solved from the second equation. Yeah, no problem. It's correct. So most people do in that way. Can you see any problem? If you do in that way, can you see something could be improved? There is some little, small problem. Very little. Not that good. Yeah. Although the whole method is correct. Whole method is correct. Yeah. So here I want to talk about one concept. Error. When we do calculation, we may have errors, right? Yeah. because we need to do approximation. We cannot avoid certain errors in our calculation. Yeah. All right. Yeah. So here, yeah. T1, yeah. So H corresponds to one half Y0, but T1 corresponds to 0.5 to a little higher than one half, right? Yeah, little higher than half. So not at half-life. That means T1 should be a number smaller than half-life, right? Yeah. Decay before half-life point. Yeah, before half-life point. Yeah. All right. Yeah. Yeah. Then the error consideration. Yeah. Error. So I want to talk about that concept. All right. If you take the first way, you calculate K first, although you can find an answer, but the error control, you may not get the best way to control the errors. Best way to control the errors. What's that? Let me explain. Let me explain the main problem here. All right. If you calculate T1 by calculating K first, that's the first way. The second way, we bypassing K. Yeah. So we do not calculate K. Yeah. Remember the previous example, we bypass C, right? Constant C. Yeah, we find a smart way to bypass constant C. Here, can we use the similar smart way to bypass K? If you can do that, because you skip calculating little k, that means you skip one step. That may cause some error. When you calculate little k, there is some error, right? Okay? Yeah. Every step, there is a possible error term. Yeah. So here, I want to talk about this error reduction in calculation. This question. Yeah. So we want to find a way to make our error as small as possible. Okay? Yeah? Yeah. For engineering people, we want to make our final result as accurate as possible, right? Yeah? So you do your best to make your final result as accurate as possible. Here, that's our effort to do that. Errors are accumulated. If you have multiple steps, each step may cause some error, right? Error 1, error 2, error 3, that accumulated. Okay? When you combine all the steps, you accumulate a lot of errors, right? Yeah. So you want to skip some, if you can skip some steps, then the accumulation of the errors will be smaller, right? Yeah, because you skip some unnecessary steps. You can reduce the total error, right? Yeah, that's the idea. So, yeah, we produce an error, and yeah, but because when we use computer to do the calculation, computer has rounding errors. The computer, the number of digits, finite number of digits, right? Yeah. So every step, you have some error. Yeah. So not very accurate. Each step, there is an error. Okay? Yeah. You cannot avoid it. Yeah. Yeah. So our strategy, we want to eliminate unnecessary intermediate steps to avoid certain errors. Yeah. Here, yeah, let me use last few minutes to show you the idea. How to try to eliminate the k. We don't want to calculate k. So we can save part of the errors, right? Yeah, part of the errors. Yeah. So we can avoid avoid, not save part of the errors. First equation from the half-life. Second equation, our target equation. Okay? Yeah. Can we cancel out K? Yeah. We don't want to do calculation on K. So how to cancel? How to cancel that K? Yeah. Let's take natural log on both equations. Yeah, base E. So we take natural log. So we don't have the base E. Yeah. KH equals natural log of 0.5 for first equation. Second equation, K times T1 equals natural log of 0.525. Now, can you see how to cancel K? Yeah. It's easy, right? Do division between these two equations. Do division directly. The top one over the bottom one. K is gone, right? Do division. Yeah. So when we do division, after we cancel out little k, we have T1 over capital H equals the ratio of these two natural log numbers. Yeah. Here, I do the opposite, just for convenience. Because I want to put the unknown, T1 is unknown. I want to put an unknown number on top for convenience. Yeah? Okay? Yeah? Because our goal, we want to write expression for T1. T1 expression. Here you can see that is our final expression for T1. And this is our formula. Yeah. This formula, before we use our computer to do the calculation, in last step, then we apply our computer, software, calculator to do the final calculation. Approximately 0.93 capital H. Capital H given, right? Yeah. So approximately 5,315 years. Yeah. That's the estimate of that OT mummy. Yeah. That's the method. Radiocarbon dating method. Yeah. In this example, people applied that radiocarbon dating method. Okay?